Let's look at arrays in C. This statement right here declares a 4-element array of unsigned 8-bit data with the array initialized to these values. The next C line declares a pointer to unsigned 8-bit data. If we want to see where this is stored in memory, and assuming that we begin storing values at location 800, these first 2 bytes, 0, 5, and AB, are stored in the first word of memory, which corresponds to the first 2 array elements, x of 0 and x of 1. C arrays or begin indexing at 0. Note that this byte location here is the memory address 0801. These next 2 bytes, 72 and 36, correspond to array elements 2 and 3 and are stored on the next word of memory. This is location 802. This is location 803. Finally, the next word of memory here is going to contain our pointer. Recall that all pointers are 16 bits, and currently it's not initialized to anything. This statement here copies array element x of 1 to x of 2. In memory, this is going to correspond to the following. Array element x of 1 is sitting here. It's at location 801, and that's going to be copied to array element x of 2, which is the least significant byte of 802. So 802 is now going to contain the 8-bit value AB. The C statement here assigns to our pointer y the address of array element x of 2. What is the address of array element x of 2? Array element x of 2 is the byte address 802, so 802 will be written to our pointer variable location here. This C statement here increments our pointer variable y using the plus plus operator. When we increment that by 1, recall what is actually happening is that 1 is multiplied by size of whatever data type the pointer variable is pointing to. In this case, it's size of unsigned int 8 bits. The size in bytes of this data type is 1. So 1 times 1 is 1. So the pointer variable is being incremented by a value of only 1. So here, if we look at memory location that corresponds to our pointer variable y, it's being incremented by 1 here. So the new value is going to be 803. The C example here is the same as the previous, except we replaced the uint8 data type with uint 16 data types. So let's see how this changes in terms of memory locations. Here, the first word is going to be corresponding to x of 0, because each of these is going to be 2 bytes wide, or 1 word. Location 802 is going to be x of 1, 804 x of 2, 806 x of 3. This next word is going to be where we're going to store our pointer variable. This line copies x of 1 to x of 2, so x of 1 is the value C9F5, and it's copied here to x of 2, so the new value of x of 2 is C9F5, which is stored at location 804. Statement 2 is going to assign to our pointer variable y the address of array element x of 2. Array element x of 2 is sitting at location 804, which means that the new value of our pointer variable is going to be 804 after this assignment has been done. C statement 3 is incrementing our pointer variable y using the plus plus operator. When we increment it by 1, we're actually multiplying that 1 by the size of the data type it's pointing at, which in this case is uint 16. The size of this data type in bytes is 2, so the numerical value that's being added to our pointer variable y is actually 1 times 2, or 2. Over here in memory, our y pointer value was 804. We're now adding 2 to it, so its new value is going to be 806. Note that variable y was pointing at array element 2, so it was pointing at this memory location here, 804. When we incremented it here, that's going to cause it to point to the next array element, which is sitting at 806, which is why it's actually being physically incremented by 2, even though in the C code we're only saying incremented by 1. The C code here declares 3 arrays, A, B, and C. Each of them have 10 elements of 16-bit unsigned data. This for loop here is going to iterate over the elements of the array, and it's going to sum the array element A to the array element B and place the result in array C. When we implement this C code in PIC24 assembly, we're first going to reserve space for our 3 arrays. Each element is 16 bits or 2 bytes, so the space needed for array A is going to be 10 times 2 or 20 bytes total. Same for B and same for C. When we implement this C code here, we're going to use these working registers for these purposes. W1 is going to be used to point at array A, W2 at array B, W3 at array C, and this loop counter here, which is I, is going to be, we're going to use W4 to implement that. Our code is going to begin by initializing these registers. So we're going to move the address of array A into W1, the address of array B into W2, the address of array C into W3. We now need to initialize our loop counter I, so we'll do a clear.byte of W4. We now need to implement this test at the top of our loop, so we need to compare I against 10, so we'll do a compare .byte of W4 against 10. What branch do we need? This branch here, we call that for, this is essentially a while loop, we need the false condition here. The false condition here is going to be I less than, greater than or equal to 10. If I is greater than or equal to 10, we're going to skip to the end of our loop and exit the loop. If that branch is not taken, then it means that I is less than 10. We now need to implement this loop body. Recall that W1 is pointing to array A, W2 to B, and W3 to C. So we're planning to use indirect addressing modes to actually access these array elements. The loop body says to take array element A, add it to B, and store the result in array element C. You would think that in order to implement this, we could simply use something like this. Add, let's grab array element 1 by using W1 indirect. Also grab array element B by using W2 indirect, add those two together, and then store that to array element C using W3 indirect. You would also think that we'd be able to use auto increment here to point to the next array element. Unfortunately, this addressing mode here is not available for this operand of the add instruction, so we have to actually implement this, what we want to do here, in 2 instructions. We're first going to move the array element A to W0 and then increment our array element pointer, array element A pointer W1. Recall that this plus plus will increment after this move is done, and then it's going to increment by 2 because this is a word operation, which is the right thing to do because our next array element is going to be sitting 2 byte locations away. We now have our array element A in W0, so we're going to add array element A to array element B and then store the result in array element C using W3. Notice that these also use the auto increment mode here, so that after we execute these instructions, C will have the new value, and all of these pointers here will point at the next array element. At that point, all we have to do is increment our loop counter I, which is being implemented by W4. So we'll increment W4, store the result back into W4, and then we're going to branch back up to the top of our loop to do all of this again. At that point, our code solution is finished. Let's take a look at C strings, which are implemented as 8-bit arrays. So a C string we're going to declare like this, in which we're going to assign a string value here, hello, to an array, which we're going to leave the array size unspecified. It will simply be big enough to accommodate this C string. We'll declare it as a data type char. Because this is going to be ASCII characters that are to be stored in this array. Here we're also going to declare a pointer to character data type. In terms of memory, let's see how memory is initialized. Each of these are going to be encoded as their ASCII equivalent, ASCII code equivalent. So a capital H is actually going to be a 48. The least significant byte of 800 is going to contain this capital H. The next letter, lowercase e, is a 65. So this word location 800 is going to contain the first 2 characters of this string. Location 802 is going to contain the next two characters, LL, which are both 6C. Finally, this last character here, O, is going to be at the least good byte of 804, which is going to be the 6F. Finally, one extra location is allocated for this C string. The last byte in a C string is going to be initialized to the null value, which is 0. That marks the end of a string. So anytime I initialize a C string like a character array like this, the end of the string is always going to be marked by the compiler with the 0, and space will be allocated for that null byte. We need that so that when we write code that processes a C string, we want to be able to tell when we get to the end of a string, and we know that we're at the end of a C string because of this null character or 0 byte stored at the end of the string. So even though it looks like that this array here has 1, 2, 3, 4, 5 bytes in it, it actually has 6 bytes once you count this null byte. So these 6 bytes take up 3 words of memory. Our C code here is going to loop over each character in the string, and if it's a lowercase character, it's going to convert it to uppercase. It's going to do this by taking our pointer and assigning it to the address of our first element in this C string. This while loop is then going to say while that character, whatever our pointer is pointing at, while it's not 0, while we are not at the end of the string, let's execute the if body. This if test here is going to check to see if this character is a lowercase character. We do that by checking if it's greater than 60 or less than 7b. If we get to the if body here, we know it's a lowercase character, so we want to convert it to an uppercase, and we do this by subtracting 20 from that character. We'll then increment our pointer to point to the next character in the string. To implement this code, we're going to use W0 to hold our pointer variable x. W1 is going to be our current character that we're processing, and W2 is going to be a temporary register. The first thing we need to do is initialize x to point to the beginning of our string. So we'll move the label value that indicates the beginning of our string to W0. So W0 now contains the starting address of our array. At this point, we now need to implement this condition test here. We're checking to see if our current character is not equal to 0. So we're first of all going to move what W0 is pointing at into W1. That's going to move our current character into W1. We're then going to compare that character against 0. This condition test, we need the false test to exit the loop. So if this character is equal to 0, we're going to skip the loop. So this branch on 0 being true is going to branch to the end of our loop and skip the loop if the character is 0. If we do not take that branch, that means that our character is not equal to 0 and will continue with the loop body. We now need to implement our loop body. So first thing we're going to do, we're going to implement this if condition test. This is using a logical AND here. Recall that we're going to do, the way that we approach this is that we do this condition test first. If it's false, we're going to exit the if body. So we need to compare our current character against 60. So we're going to move 60 to W2. Our current character is sitting in W1. We'll do the comparison. We need the false test to skip the if body. If this is false, so the false test is going to be a less than or equal. So we'll do a branch on less than or equal to end if to skip the if body. If this branch is not taken, then we need to do this next comparison here, which is going to compare our current character against 7b. So we'll move 7b into W2. We'll compare our current character in W1 to W2. The false test here for this is going to be a greater than or equal unsigned. So we need to do a branch on greater than or equal to unsigned to NF. If neither of these branches are taken, then it means that we can execute the if body. So to implement our if body, we're going to take our current character, subtract 20 from it, and store it back at our array location. So we're going to move 20 into W2. We'll subtract that hex 20 in W2 from our current character in W1, and we're going to store it back into our array. Remember that W0 is used to point at our string array. At this point, we have converted that character to an uppercase. At the end of our if body, we need to increment our pointer. So we're going to increment W0, store the result back in W0. We only increment it by 1 because this array has byte values in it, which represent the ASCII string values. At that point, we're now going to branch back to the top of our loop and do all this again, and we are finished with this code solution.